Hello, my name is Evelyn Bravo, and this is my presentation for Lab 3, Black Holes and Orbits, for Physics 1. So, the purpose of Part 1 of the lab is to analyze the motion of a star when in orbit around a black hole, and then use this information to determine the mass of the black hole. So for Part 2, the purpose is finding the net force of the moon and spaceship to determine what velocity is necessary to get close to a planet without crashing into it, yet remaining in orbit. Some related fundamental principles of physics for this lab would be Newton's second law, the gravitational force or the constant gravitational force, the velocity update formula, and the position update formula. So for Part 1, the procedure would be step 1, using the velocity components given, find the initial and final velocities of the star, then use this information to compute the initial and final momentum vectors. Then we're going to calculate the F-net of the star and then calculate the mass of the black hole. And computationally, while this code is running, the star's velocity and position is going to be updating as it orbits the black star, and we're going to be using the velocity update formula and the position update formula to do this. So you can kind of see these steps reflected in the code to the right here in the image. So some initial conditions for this part. So we had to use a gravitational constant, which is 6.7 e to the negative 11. We had to use the mass of the star and delta T, which you can see in this code to establish the foundation of the initial conditions. And then so for the observed data, based on the data collected, the mass of the star would be 6.9 e to the 33. And then we also were able to calculate the F-net parallel, and then the F-net perpendicular. And then this image kind of just shows the star's position as it completes the first orbit around the black hole. And then that is then used to calculate the mass, which we just talked about. So for the lab procedure for Part 2, we have to find the net force on the moon by the planet. We use the same steps to find the net force on the moon by the spaceship, and then we use these findings to calculate and update the position and velocity of the moon, as well as the position and velocity of the spaceship, which can be seen in the code to the right. So some initial conditions for Part 2, we use the same gravitational constant as we did in Part 1, but some additional information that we get is the mass of the planet, the mass of the moon, and the mass of the spaceship, and of course delta T, which we can see the initial conditions placed in the code to the right. So for the observed data, based on the data collected, the moon's orbital speed would be 2.4 e to the 4th meters per second, and then the moon's orbital period is an estimated 64 hours. So due to trial and error, the figure 8 was not able to be achieved for the spaceship due to just human trial and error for this specific data set. So possible errors would be that although this data was found computationally, it is still a simulation. Therefore, the results will not necessarily be accurate representation of reality. Also because we're using very limited forces and isolating the system and the surroundings. Also, trial and error, as I mentioned, was used to find the velocities of the objects. Therefore, if results are not what is expected, it is due to human error. What does this mean, and what if? How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So the net force and the rate of change are equivalent. However, the way of reaching that solution is a little bit different. So to calculate the net force, you need to know the masses of every factor exerting a force on the system, as well as all the components of those factors. However, to calculate the rate of change, you just need to know the change in velocities of the system. So calculating the net force is a little bit more complicated than calculating the rate of change. And then for what if this imaginary system has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? So you would need to include initial conditions of the planet, as well as the net force of the black hole on the system. Thank you. And that is my presentation.